This is a great example of a problem that's going to ask us to rank acids and bases according to their strength. Now we can do this a couple of different ways. Here we're given Ka values for some common acids. We might also end up kind of using our noggin a little bit. Let's see what we got here. Water. Okay, I normally don't think of water as a very strong acid or base. HF, hydrofluoric. I should recognize that as a weak acid, and I should find it on this chart with a pretty small K value, 10 to the negative 4th. What else do we have here? Hydrochloric. Notice that it's really not on this chart. All of these would be considered weak acids. They all have pretty small K values. Now notice that they list them in increasing strength at the top, because at least it has the largest K value with that hydrogen sulfate ion. And if K values are products over reactants, the larger the K value, the more this thing shifts forward to produce ions. When you get down to the bottom and you have K values like 10 to the negative 10th, it really is primarily neutral particles. Do they shift forward? Not by much. Okay, so let's make note of a couple things here. This one I do have a K value for. Hydrofluoric. Let's write that one down. Ka. It's pretty small, 7.2 times 10 to the negative 4. Do I know a dissociation constant for water? I mean, I do know that water tends to self-ionize, and it does have the ability to produce an acidic particle, H3O plus 1. Do we know to what extent water ionizes? Yes, we do! It's a constant. The Kw of water is about 1.0 times 10 to the negative 14th. Okay, so does water form an acidic particle? Sure. But again, not by much. The dissociation constant for water is even smaller than some of these very weak acids. Notice HCl, again, it's not on this list because it's a strong acid. HCl is a strong acid. It almost dissociates 100%. Its K value is really like 1 point something times 10 to the positive 8th. It's giant, which often then they don't even list it on these charts, because for a strong acid then we will assume that it dissociates 100%. HNO2, I believe we have nitrous acid. There it is. So let's get that guy down. Ka is nitrous acid, 4.0 times 10 to the negative 4. And this guy, HCN. Yep, hydrocyanic acid. Oh boy, that one's small. 6.2 times 10 to the negative 10. Ka times 10 to the negative 10. Okay, so I think we should be able to rank these then in order of, let's see, strength as acids. Well, the weakest acid of all these should obviously be the water then, right? It's got the smallest dissociation constant. Let's list water first. Water is the weakest. From there, we're going to go by K values for these weak acids. So the smallest K value is this guy, HCN. He's the next weakest acid. The next smallest should be the hydrofluoric. Then I would have the HNO2. And the strongest is obviously the HCl. Again, they don't even list a K value. It really is giant. It's like 1 point something times 10 to the 8th power, Ka. It's huge. Again, they often don't even put it on charts because we'll assume that it dissociates 100%. Well, that wasn't so bad, right? We're primarily using these K values to rank in order of increasing strength. The larger the K value, the more likely it is to dissociate. Now, things can get a little funky when we move to the bottom. And now they want us to arrange the following in order of their strength as bases. Okay, so we see water again, which we know water can go both ways. It can either be acidic or basic. The rest of these are the conjugate bases. Okay, so let's look at this guy. This is the conjugate base of HF. If this guy is produced and we want to send it in reverse, then this fluorine ion needs to pick up hydrogen. If you're accepting hydrogen, you're acting like a base. Chlorine is the conjugate base of HCl. The nitrate is the conjugate base of the HNO2. And this guy is the conjugate base of the HCN, hydrogen cyanide. Okay, cool. So we have a couple options. We could kind of do this qualitatively, or we could do this quantitatively. And again, I do kind of want to compare K values, but now I want to think about them opposite in order of strength as bases. Well, what's given in this chart, these are Ka values. But we could switch a Ka to a Kb. So if I wanted to do this quantitatively, here's my option. Kw equals Ka times Kb. This equation is given in your packet. Times Kb. Quantitatively, you could use it in a situation like this, where let's say I wanted to change these Ka values to Kb values. So of the ones listed on the chart, I know Kw, and we could actually still put that in for water. Kw is 1.0 times 10 to the negative 14th. That's its dissociation constant, whether we're thinking about it acidic or basic, because we're going to get one basic particle and one acidic particle. Okay, so if I take that Kw, and now let's plug in a Ka value. So, for example, here would be hydrofluoric. Let's do hydrofluoric. I would say 1.0 times 10 to the negative 14th equals, the Ka value is 7.2 times 10 to the negative 4th times Kb. Kb. Gotta sneak it in there. And then all we have to do is rearrange this and solve for Kb. So it's a useful equation. It kind of lets us switch between acid constants and base constants. Kw is always 10 to the negative 14th. So let's see what we get here. 1 times 10 to the negative 14th. Let's divide by 7.2 times 10 to the negative 4th. And bingo. Here's your Kb. The Kb of the conjugate base, the fluorine ion, is about 1.4 times 10 to the negative 11th. Whew, small. All right, so now what if we do this for all the rest of them? Okay, let's try this. Let's do the Kb of, let's go down the line, NO2. So I'm going to do the same thing. I'm going to take Kw, 1 times 10 to the negative 14th, and divide by the Ka value. So for this nitrous acid, it would be 4.0 times 10 to the negative 4th. And I would get 2.5 times 10 to the negative 11th. And then let's do this same thing, Kb of the cyanide ion. I mean, all these have the ability to pick up hydrogen from the solution. So all of these ions should be basic. They're negative ions that can react with hydrogen, and they form weak acids, which means they really don't dissociate by much. Okay, so let's do this guy. 1 times 10 to the negative 14th divided by 6.2 times 10 to the negative 10th. And I would say like 1.6 times 10 to the negative 5th. All right. So we got a couple of these. Now we've got Kb values, which again, we'll just rank them in order of increasing Kb value. That ranks them in order of increasing strength as bases. There's just one that I don't have listed. The chlorine ion. Which again, we could kind of do the same thing. I could kind of do this with chlorine. Cl-. Let's say we plug in the Ka value as, let's just do this. Let's use Ka for hydrochloric acid as 1 times 10 to the positive 8th. Okay, so let's calculate Kb then for chlorine, the conjugate base. 1 times 10 to the negative 14th divided by about 1 times 10 to the positive 8th. Oh, okay, interesting. Divided by 1 times 10 to the 8th. I get about like 1 times 10 to the negative 22nd. Okay, so quantitatively, here's what we could do. We could use that equation to switch between a Ka and a Kb. Now I'm looking at the conjugate bases of those original acids. We can rank them in order of strength. The weakest of all these bases then, the loser of the bunch, is the chlorine ion. Next smallest, water. The next loser. The next smallest would be the fluorine ion, followed by nitrite, fluorine ion, nitrite, NO2, and then finally the winner, I guess, is the cyanide ion. Okay, interesting. Now part of this kind of reflects these guys. Like, look at these weak acids in the middle. We had this hydrogen cyanide listed as the weakest of the weak acids. So it doesn't go forward by much. Well, then look at the bottom here. This ends up being like your strongest base. This guy really wants the hydrogen. He really wants the hydrogen. This thing, the cyanide ion, really tends to stay as HCN in solution. This guy does not have a tendency to ionize by much, which means it's a stronger base. Okay, so then these guys kind of go in reverse. Of these weak acids, HF was the strongest, which means it has the tendency to go forward the most of the 3 weak acids. So then this fluorine ion is the weakest base. Some of that HF really does stay in solution. So does all of the fluorine pick up hydrogen? Not all of it. Some of it stays dissociated. The only two that sometimes aren't real obvious are the chlorine and the water. But again, the chlorine is the conjugate base of a strong acid, which means it stays dissociated 100%. Does the chlorine pick up hydrogen and send us back to neutral HCl molecules? Not really. I mean, again, the dissociation constant for the acid was so high. It was like 10 to the positive 8th power. Virtually all the chlorine stays as chlorine ion, and it really does not pick up hydrogen and go backwards. So that chlorine is the weakest base. He will not pick up hydrogen. Next comes the water. I mean, water is a weak acid and it's a weak base. The dissociation constant is really small in either direction. But we're going to say that the chlorine ion is an even weaker base because it's coming from a strong acid. That chlorine ion does not pick up any hydrogen. It stays as chlorine ions. So again, you could do this quantitatively. You could go through and recalculate all the Kb values and then again just rank them. Or you can kind of do it qualitatively. If I have the conjugate base of a strong acid, it's a really, 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 really weak base. And then as I go toward weaker acids, the conjugate base must be stronger. Like that cyanide ion, that guy really does have a good tendency of picking up hydrogen from the solution. Because if that's the weakest acid, HCN, most of that cyanide reacts with hydrogen. Most of the cyanide is acting like a base. So either qualitatively, which would maybe be more of a multiple choice question, or quantitatively, maybe I would calculate the new KBs. But either way, we can rank these acids or bases using their dissociation values. And again, a little bit of common sense when it comes to like a strong acid and something like water.